In today's lecture, we are going to look at sequential games. So up to now, the games that we have looked at were simultaneous move games. So in it, the players moved at the same time. Players were not aware of the actions of other players when they made their moves. But in some games, the order of moves matters. And these are the sequential games. In sequential games, a player who moves later in the game can observe players who have played up to that moment. And information from observations can influence strategy. And the player's strategy will then be a contingent plan dependent on the actions taken by other players. So we're going to look at the sequential battle of the sexes. We're already familiar with the simultaneous move version of the game. And when the game is played sequentially, the husband and wife do not make simultaneous moves. The wife moves first, choosing either ballet or boxing. The husband then observes and decides how to respond. Now, the wife has two pure strategies, boxing and ballet. However, the husband's strategy set will expand. So let's look at the husband's contingent strategies. So the husband could always go to the ballet, and in conditional notation, with the husband's action first, we have the husband goes to the ballet, given wife goes to ballet as well. And the husband goes to the ballet, given that the wife goes to boxing. So always go to ballet for the husband. The husband could follow the wife, right? So he would go to ballet if she went to ballet, and he would go to boxing if she went to boxing. The husband could do the opposite. So the husband would go to the ballet if the wife, the husband would go to the boxing if the wife went to the ballet, and the husband would go to ballet if the wife went to boxing. Or the husband could always go to boxing. So the husband goes to boxing if wife goes to ballet, and the husband goes to boxing if the wife goes to boxing. Now, some of these actions may not make rational sense given what we know from the simultaneous move game. I mean, why would the husband go to an event where the wife is not going? However, since it is a possibility, since it is an allowable strategy, we have to include it. We have to write it down, whether it makes complete sense or not. Even if it is irrational, we write down the strategy. So using this information, we construct the normal form payoff matrix. And here is the wife and her two pure actions. And here is the husband with his expanded action set. So if the wife goes to the ballet and the husband also always goes to the ballet, they will end up in the same event. And the payoff will be 2 to the wife and 1 to the husband. If the husband follows the wife and the wife goes to the ballet, then the husband will go to the ballet as well. And we have the same payoff of 2 to the wife and 1 to the husband. However, if the husband adopts a do opposite strategy, then if the wife goes to the ballet, the husband will go to the boxing. And since they are separated, they will have 0 payoffs. And of course, if the husband stubbornly always goes to boxing and the wife goes to the ballet, they would again be separated and have 0 payoffs. And we can similarly draw conclusions for when the wife goes to the boxing match, right? So if the wife goes to boxing and husband always goes to ballet, they would be separated, 0-0. If the husband follows the wife and the wife goes to boxing, the husband would also go to boxing for a payoff of 1 to the wife and 2 to the husband. If the husband is going to do the opposite and the wife goes to boxing, both will be separated and they will each receive 0 payoffs. And if the husband always goes to the boxing and the wife goes to the boxing, then they will be together with a payoff of 1 to wife and 2 to husband. And you can solve for Nash equilibria by underlining the best responses. And if you do so, you'll find 3 equilibria in pure strategies. Game theory in this instance allows us to choose among the equilibria. So let's draw the game in extensive form. And we simply remove the fence from the husband's decision node. So in the simultaneous move version of this game, there was a fence drawn around the husband's decision nodes in order to indicate that they were in the same information set. The husband does not know the wife's action, so we fenced his nodes off. Now he knows. Now he can observe what the wife's actions are and then decide upon his own actions. So we no longer have a simultaneous move game. So let's think about the game a little more. Suppose the husband wishes to go to boxing. So he quote unquote threatens his wife by saying that he will always go to boxing no matter what. Now, if the wife ignores the threat and insists on going to ballet, for example, what will the husband do? Will he still go to boxing as he had threatened to do? And the answer is no. Why? Because if the wife goes to ballet and the husband carries out his threat by going to boxing, he will end up with a payoff of 0 because they're separated, rather than a payoff of 1 if he had accompanied his wife to the ballet. Now remember, in game theory, the players always prefer higher payoffs. So if the husband is stubborn and sticks to his threat of going to boxing, even when the wife goes to ballet, the husband would get a payoff of 0. That is not acceptable. So if the wife goes to ballet, the husband will follow the wife and go to ballet in order to get a payoff of at least 1. This means that the threat by the husband is a non-credible threat or an empty threat. The threat has no meaning. And by a similar logic, if the husband or wife threatens to always go to the ballet, that would also be an empty threat. So you can think about the wife. If the wife is always threatening to go to the ballet, that would be an empty threat. If the wife is always threatening to go to boxing, that would also be an empty threat, right? Even if the husband is always threatening to go to ballet, that would be an empty threat as well, right? So empty versus credible threats. So threats that are not empty are called credible threats. They can be understood using the concept of equilibrium path, the connected path through the game tree implied by the equilibrium strategy.